distinguished professor. He's also a John Gurrow and director of the RIT Center for Computational Relativity and Gravitation, and co-director of the Space Physics Institute for Research Excellence. A little bit about her background. She got her laurea, which is a Bachelor of Degree in Mathematics from the University of Perugia, Italy, and then received her PhD in physics. Topic was quantum field theory and general relativity at the University of Bern in Switzerland. And before coming to RIT, she spent some time at the University of Texas at Brownsville. She was a Marie Curie postdoctoral research fellow at the Albert Einstein Institute, the Max Planck Institute for Gravitational Physics in Germany, and also was at the Astrophysics and Astronomy Department at the University of Tübingen, Germany, and the Physics Department at the University of Utah in Salt Lake City. So she's been around a lot of different places. I will say that in her CV that in 2024, she received the Richard Isaacson Award in Gravitational Wave Science for extraordinary contributions to and leadership in the understanding and simulation emerging binaries, compact objects, and strong field gravity. That's from the American Physical Society. About 10 years ago, she received a Trustee Scholarship Award here at RIT. And there's a whole list of other things, but she's received over $16 million in research funding while here at RIT. So with that, let's welcome Professor Campanelli.
Being here, how many of you here are graduate students, by the way, just to make a sense? A majority. Okay, I'll try to be okay. So some of the slides you will see, might be a little bit very, detailed. So don't worry about that. I'm going to walk you through the talk. Okay. First of all, thank you for having me today. As you can see, there is a little bit of imaging on everything we do. By the way, these images that you see were created by Firefly. You can instruct AI today to tell pretty much what you want to see on the screen, but they're not real simulation goals that you're seeing here. But you will see over the top real simulation. Okay, so what we are going to be talking today is some parts of my research, not all my research, but some components that are related to what Zach and I will be working on for their PhD thesis. Okay, so and we're going to be talking about supermassive black holes and understanding supermassive binary black holes in terms of what kind of lights and jets they do emit and how we go after these things. And we're going to be talking about how to unravel the physics and astrophysics of these objects, through advanced simulations. Okay. Oops, it doesn't play. Okay, let's try this. Funny. Let me try this. I'll have to click. Okay, so first of all, you see, there's quite a bit of people involved in this collaboration. Yeah, so there's a number of $1 million that were mentioned, but this often comes with the price that you have to work with a number of people, and these are the people I worked through a number of years. And you see that I have emphasized here based on the size. The grad students tends to be the bigger size, and this is Zach over here, just joined recently my group. A lot of them are actually graduate students and postdocs in the group. We use supercomputers, and everything that you're going to see through this talk has been done through the use of very large computers powered, at supercomputing centers, like, for example, the Texas Advanced Center for Computing, the TAC Frontier system, or the Oak Ridge National Lab Frontier, which is the largest supercomputer available, I think, still in the world for centimeter. All right, so after I've done the credits, I can go to the, I think I have to use this, okay, something is not working. Okay, so I have to click, unfortunately, individually on the slides. All right, I remember to do that. This is about modeling. And first of all, I want to say something about modeling. You know, we had an incredible success a few years ago when we demonstrated that we were able to essentially model pretty accurately the gravitational wave forms that were detected from the LIGO collaboration, you know, about a binary supermassive black holes. Now it's been a few years, almost, you know, it's incredible how years pass by. It's almost 10 years, but not quite, but quite close to it, right? So 2016, it was when we detected the first one. And you see in the first row there, we have the, you know, the signal that were detected by the two LIGO detectors. And below is the signal that was predicted by the calculations. And so the calculation that went actually into that plot came from, you know, a number of us, also from my group. Okay, so this is was, you know, worth a Nobel Prize, as you know, and you see here something that I often like to refer because Kip Thorne, who won the Nobel Prize for this work, he used to, you know, tease us about, you know, the fact whether we were going to calculate these things before actually gravitational waves were detected or actually no problem. It turns out, you see that we did it before, but essentially, I think we didn't get the glory until very much until these things were really confirmed. And today, the story is quite different because we have hundreds of these detentions. Okay, so this is like a butterfly plot that shows essentially binary black holes detected by LIGO, and you can see, you know, two black holes, you know, leading to one merged black hole, and you can see the masses. Okay, so you see the mass ranges of these objects. So we can go from few solar masses, the very small black holes, to the largest black holes that are 100 solar masses. Okay. When we talk about LIGO, obviously we are limited because the frequency range of these detectors, as such, that we're going to be targeted only solar masses type of systems. In this talk, I'm going to be focusing on the supermassive black holes, but I don't want to forget about what has been done in this context. Okay, so this was worth a Nobel Prize, as you see here, Kip, and I will acknowledge during his Nobel lecture, along with other colleagues, for having contributed to solving this problem. So what it took, though, I mean, although I was acknowledged, has taken really the effort of a large community behind that took decades effort to solve, right? So the Einstein's equation weren't simple, and you know, as you can see, already in 1957, most of you probably weren't even born then. Including myself, probably. You know, people already were envisioning what needed to be done, right? And I always, you know, have a little bit of amusement reading this because, and this is from Charles Misner, who died a few years ago and was, you know, wrote this amazing book on gravitation, where he predicted that there was going to be a very, you know, so you see that he kind of say, you know, we need a computer machine better than anything we have now. Many programs, and a lot of money, of course. And then you say, well, that's going to be very difficult. The program will end up shooting itself, or the machine will blow up, right? It ended up, but then neither the program shoot itself nor the machine blow up, but the code did. Okay, and that lasted for quite a decade until we solved this problem, right? And yeah, so and that's why we deserve that slide. Okay, so today we have a number of codes. It's nothing like it was then. You know, there's quite a bit of these codes here. They're all based essentially on the methods that were introduced by my collaborators and I. Okay, which is called the moving puncture. I'm not going to go into the details. It's working. Everybody's using it, and we have plenty of codes. All right, let's go down now to describe what we can do with it. Okay. So first of all, why is it important to solve the problem of binary black hole body? Well, there are black holes out there, we know now, right? There are several detections, and there are also binaries. And of the binaries, that we are interested in, you see, we are spanning a very large spectrum here. We're going from the binary that I showed you were detected by LIGO to the binary system, very large binary system at the center of galaxies, supermassive ones. And that spans different gravitational wave frequency, okay? They are related to essentially to the periods of the orbit and the masses of these objects, okay? So you look at, solar masses, we're talking about, periods of milliseconds, okay? So these things are going to merge into milliseconds. When we're going to go to the supermassive, we're going to be talking about, processes that last from hours, like 10 to the 6, 10 to the 5 solar masses, to, months, to decades, where we're talking to very large supermassive black holes, like 10 to the 9 solar masses, for example, okay? So observationally, it means that to detect these things, right? So it's still in the human time scale, right? But it can range from a variety of, observational times. Okay, so the one that we're going to be very interested for the work that Zach and I are going to be doing is mostly those that are in the range of hours to years. So as you probably know, you heard that the LISA space mission will be flying in a few years, funded mostly by the ESA, but it's already in progress. So it's going to be flying and it's going to be targeting, supermassive binary black holes. And once we do that, we're going to be able to see pretty much all of that in the universe. Also, timing array, you might have heard about that. There was a big announcement a few years ago, and I'm going to go through this as well. But, we have detected a big home in the universe, right? So we hear that there is, a lot of signals, okay, of potentially supermassive black holes. And we're going to go to this in a moment. I have to click, I believe, the slide. Okay. But, okay, how these supermassive black holes really happen to arise? They are there because we know observe them at the centers of galaxies, but we also know that galaxies do collide. We also see galaxy mergers happening, or at least, we see the remnant, and also in the process in the universe, from the beautiful images of Hubble or, now GRMHD as well. We see that there are many galaxies that undergo merger. And if galaxies undergo merger and they contain supermassive black holes at their core, they have also to go undergo merger. So how many of them are going to go to merger is a big question. People do, have recent estimates, depending on the masses, depending on the depth. Okay, you might expect that, for example, in the LISA range, you can run between 1 to 200 of them merging every year in the sensitivity detectors. So it depends on what type of supermassive black holes are you looking at, and what type of detectors. But you're gonna be targeting these things. Okay, so the problem is that we don't yet have signals. So although we have signal value, we do not have it until these detectors are going to fly. And so what happens? We know what happens mostly by theoretical means. So we can predict that they are going to merge, essentially reach supermassive scale, merge, and then through processes like dynamical setup of friction or gas exerted torques from the gas exerted will extract, angular momentum from the system, and the binary black holes tends to merge, and then eventually gravitational radiation will carry away energy And the Einstein's equation will tell you that they're already extreme, and these things will smash into each other at the end. Okay, so at that point, you know, a lot of gravitational waves are going to get in. And hopefully Lisa and PA would tell us all about that. But because these things were actually immersed in a very gaseous environment, they should also emit a lot of light. Okay. So lights, jets, and they should be very, very bright. And you know, you can kind of estimate that, you know, the luminosity of these things, you know, will go roughly as, you know, the accretion rate based on the, you know, the system and where this m dot, or you know, m related to m squared to the black hole. So we're talking about, you know, more than 10 to the 47 Earth second. Okay, so very energetic systems. Okay, so here I have a cartoon about the whole process, and you can see, you know, you go from galaxy mergers that are kiloparsec separated down to things that are subparsec, and when it reached to this regime here, you're already emitting, you know, significant gravitational waves, and should be detectable already here. But as the gravitational wave emission goes, you know, they end up merging a lot of gravitational waves here. And then finally, after they merge, you know, some of these systems, if they merge in a way that it's the gravitational wave is not isotropically emitted, they can also get a kick imparted by the gravitational waves at the end, and that kind of expelled the black holes out of their whole structure. So this is another work that we did in 2006, where we predicted these gravitational wave recoil, and you know, there's another potential signature we might be after. But you see, it spans from kiloparsecs to something which we call RG, which is essentially the Schwarzschild rate. So it's a huge dynamical range, okay, the scales. Okay. So it's obvious that we cannot do this in single simulations, okay? And what people do in the community, they do different, you know, we study these different stages, and then we connect the dots, okay? What what my group and I do, deal with these last stages, and we take information from these other stages, starting today. Okay, so what I'm going to show you here are what's happening in the last stages. I don't know why I have to click here. All right, so I think I already mentioned that. So I'm going to cover that fairly quickly. You know, you might have heard again about the nanograv, you know, detection, the harm that we hear from the universe, you know, and you see the correlation pattern, the 15-year correlation data. And it seems that, you know, this favor the fact that this could be coming from binary supermassive black. The news were that, and I erased that slide because it's very detailed, but you might have heard just about a month ago or so, there were new results from NERCAT that essentially might be able to now even tell us that the signal will be localized from a particular region in the universe, which would be extremely interesting if that is the case, because we would be able to target that system. Because this signal, you know, we doesn't tell anything where it's coming from. This, you know, gravitational wave correlation pattern, and it's all over the sky. But it's very loud. Okay, so please feel free to ask questions for clarification if you think I'm going too deep into astrophysics or physics. I'm trying to make it as simple as possible. Okay, so I talked about gravitational waves. I talked about electromagnetic waves. So they're different signals, okay? But the supermassive binary black holes do emit both of them. And that's extremely interesting because then you can do what is called multi-messenger astronomy. What is it? multi-mass neutrality is taking into account both information in an integrated way so that you can learn the most from the system, right? Because gravitational waves are going to carry the information about the object themselves, the masses of the supermassive black holes, how far they are, the characteristic of the orbits, how fast they rotate, okay? All of that information is in the gravitational waves. But photons tells you everything about the gas swirling around, the jets, okay? All of that, you know. So combining this information will give us a great deal of information about the environment of these objects. Yes.
Are those information correlated with each other?
Some people are trying to correlate. The big problem right now is that, you know, we are trying to provide models, okay, or if you want, you know, calculation of what the signal will look like for the electromagnetic counterparts, okay. For gravitational waves, you have to solve the Einstein's equations, and those waveforms that we produce for LIGO are pretty much very similar. They scale with the ones, okay? So that is well understood, and all we need there is for LISA to fly, and for PTA, for a timing array to get more sensitive, okay? That's all we need there. For electromagnetic signals, it's a mess, because when you get mother, it's much more complicated. Now you have generativity, you have mother together, and you have to solve all the systems together. So we do not know exactly yet, but we are making tremendous progress, and with my team leading the way down in that direction. Okay, so that's what exactly I want to do. I want to provide, you know, what the signal will look like for the perspective, so that we can combine the information and see if there is any correlation. So the answer is maybe there is, but we do not know. So on this slide, I just wanted to offer you the perspective also that, you know, what there's LISA, there's PTA, but there's also a lot of other missions that are going to give us information in the electromagnetic spectrum, right? So I just mentioned here a few, and you can see they span really across many, you know, type of solar masses and, you know, distances, right, redshift and so on. So we're going to cover pretty much a lot of the universe. So we're going to be able to understand a lot, and maybe I'm not going to go to details here because there are a lot of details of, you know, where these things might occur, and it's all about theoretical right now. And, you know, people think that they are present in quasars. You know, we can see, in fact, signals, and let me just show you the next slides. If I can change that. So now the question you have now, can we really see that right now? It's hard also from the point of view observationally to see that now, but there are some signals out there, okay, that are perfect, let's say perfect, not perfect. They are good candidates, okay, for supermassive black holes from the electromagnetic point of view, okay. There are a few of them here. I have just a few in my slides. There are more than that, you know, hundreds of them, okay. The question is, though, without knowing exactly what happened and what the signal looked like, this is always going to be more subject to interpretation, okay? But here you go. So this is one of the oldest one. This is OJ287, right? This is 1 to 100 mass ratio things. You see periodic flare of an object passing by 11 years, every 11 years. This has been observed for, now look at the, you know, look at the time when it started to be observed. You have very few data then, but now we have much more data, right? So this has been the most observed thing ever, okay? That might indicate the presence of a supermassive black holes, and still people over, you know, well, it's almost a century or more there of observations, still this is being interpreted as such, as a supermassive black hole. So there are other observations you can do with, you know, look at the double nuclear, this particular system here. I put it on, I mean, they're all dual AGNs, but this is, I think, has the two you know, nuclei fairly close, that they are in the weakly gravitational wave regime, so they're relatively close. You can look at other things like sinusoidal light curves, okay? So when you detect light curves, you can look whether there's periodic signals. You got to be careful though, because a lot of things are periodics. So you got to be careful about this interpretation. There's other interpretation. People are looking at things like self-lensing. So they look at this kind of blip, okay? The black holes themselves can act as lenses because they distort the space-time. So when a black hole goes in front of the other one as they orbit like this, it will lens the light, okay? So that lensing will result into particular peaks in the light, okay? And so that is another way, and people are very excited about that because that's really related to very closely to what the space-time does to light passing very close to the black hole. Will be a clear solution if that. So there's been a few candidates there. And I mentioned quasars. This is another interesting image. Okay, this is a 12 kiloparsec separated image, but I forgot the masses, but these were pretty high masses, you know. So, and there's a very distant object. But it's so distant, but look, they can really, you know, see that. So, okay. So there are some candidates out there, but we need theory to really tell a little bit better what really to expect. And we, so I'm going to skip the recaller for now. I've done a lot of work in that arena. This is the latest stage, but I'm going to focus mostly on the merger itself. So therefore we need to have models. So there are kind of other observation I want to mention, because this was an observation by a graduate student in the UST program. She gave it to me, and because this is you know been done in the context of looking at line shifts, and you see that you know she gets you know from interpreting from this graph she can get you know that you know maybe the gas was moving you know or either the gas or the binary black hole moving the gas around, so you know was moving at really high speeds. Okay, so high speeds that these were kind of moving at a quarter of the speed of light. So what else can be done? That nothing in the accretion disk you know itself of a single black hole can do that. So maybe it's a binary. She was wondering it was a maybe recording black hole, and I told her no, that can't be, because the recording black holes are going to be moving at maximum you know 1,000 kilometers per second. Okay, so but we need theory. Okay, so we need to model that. So I have that little joke there, right? So unless we want to do like in that joke, we have to have really this. All right. Okay. So okay, what we do? Even in theory, things are not perfect because you have to make assumptions. And as I say, we have very large dynamical scales to cover, but I don't have to do it all, you know, myself or my students. I can just, you know, take information from simulations that are done in the kiloparsec range and then incorporate it in my models and then proceed with modeling the latest stage of the coalescence and merger. And you see, these are more or less, I mean, what do you do? What kind of models are there? People assume that maybe the gas around the binary can be more like stars around like a gas cloud. Okay, and again, this is created by Adobe, not by the simulation, right? So instead of making a sketch myself, I ask it, yeah, I can make it for myself. But okay, so this is kind of illustrating, you know, maybe you have gas around, you know, the system, and it's, you know, a gas cloud, all right? Or you have actually a circumbinary, right? Like you see in circumbinary or circumstellar, right? So you have gas around it, and maybe it's arranged like in, you know, like a torus, and it's accreting around the black holes, and they form, you know, this mini disk around each of the black holes, right? So in the simulation that I'm going to show you, we're going to mostly use this one. which is actually the more complex simulation. People have done also these, but these are harder to simulate, but we're going to focus on that one. And there are many other parameters that you have to take into account when you do simulation. Obviously, the masses of the objects, the accretion rate, the characteristic of these accretion disks, and so on. There's quite a lot of things to vary and change. Okay, and a lot of also what happens depends really on the balance of heating and cooling mechanism. You know, how much this gas, get cooled by photons that gets emitted and transported within the gas, interacting with the gas gets eventually ionized, how you model that, and then once the photons gets into, above the corona, what they do, they pretty move it there, how you describe what kind of radiation coming from there. So it's a fairly complex problem, but we don't do it all at once. We split the pieces and work on different aspects we're going to see. So the equations, okay. If you like math, you're going to have fun here. Many of you know about tensors. I'm really writing all this down in a tensor notation so it can fit in one slide. But so you know the Einstein's equations. You've heard about them. Here they are in a tensor form. The left-hand side express the space-time, and the right-hand side is the matter feeding into the space-time, right? They are non-linear, they're coupled, right? So as Wheeler used to say, matter tells how the space-time occurs, okay? And the space-time tells how matter to move. So it's all in between. It's all, okay, so there are heavily non-linear equations, more than 10 equations. When you choose the variables that, you can put in a computer and evolve state, it's usually up in more than 20 equations, okay? It evolves. Then the conservation energy momentum, conservation of rest mass, for the Euler equations, and so on, the hydrodynamics equation, the moment equation, the energy equation, you're familiar with those. I'm actually teaching this course right now. Advertising my course. If you want to come and learn some fluid dynamics as well as relativity. So, and the Maxwell's equations, they're all coupled. And finally, there's another piece, the radiation. And radiation is a big, because radiation, if you want to follow what happens to radiation, then really you have to solve the full Maxwell's equation system, and that's how you design it. So the system is fairly complicated. So that's why you need supercomputers.
It doesn't look at a wave equation. Where is wave equation?
Some of these things that can be rewritten in terms of wave equations. They're very similar, but they're complicated wave equations. The way we recast these equations, okay, are mostly wave equations. But complicated wave equation with a complicated source term. They're coupled system of nonlinear wave equations with complicated source term. Highly coupled, and many of them. All right.
But still, it's the basic form of a wave equation, second derivatives of time, space, and a loss term, perhaps.
Some of the equation, yes. But the Einstein's equation also, as they're written over there, they include, they can be decoupled, or not decoupled, but can be kind of separated into something which is called evolution equation that look like more wave equations, and equations that are elliptical, and so they're kind of constraining the initial data. So in relativity, we have certain freedom to give initial conditions, but these are constraints by the Einstein's equation. So we're not totally free. Okay, so we have additional equations. In addition to that, if you want to have more fun, because we do not know how to write these equations in a coordinate system, because the thing is, well, they're moving. We call these dynamical gauges. So we solve for dynamical layers. The coordinates are changing over time, and we have more equations to solve. All right, so it's fairly, it can get fairly complicated if you want to go down this route. You really want to go down this route, we can talk later. Okay. I just want to say that, okay, we're doing a lot here, but it's been working in the community. But it's pretty recent. You can see, you know, some of the first simulation exploring what happened in the vicinity of supermassive black holes and doing hydrodynamics equations. We're done first in 1D using Newtonian gravity. And then, you know, people were finding that there were gravitational force expelling the gas out of the system, and they say, well, there's really no gas in there, you know, there's no signal. It's pretty much what people actually believed, even up to 2008. I remember when Caltech talked to Kip Thorne and Dr. Feeney up there, and asked him, you know, because he's one of the co-author speakers. I said, you know, I want to do 3D simulation. What Kip Thorne was a space-time guy and writing me, I was very excited. You know, they're going, oh, you're not going to find anything. Well, things changed. In fact, we did find that there is a lot of gas that gets into what is called the cavity. There's no more cavity. This gas gets into forming these mini disks, okay, around each of the black holes. And gas accrete to streams, that you can see. We're going to see some of these simulations that kind of change the picture. And now in the community, it's pretty understood that indeed there is enough gas down there to make these things electromagnetically, you know, loud. Just okay, so there are a lot of details, and tell me, I tend to go a little bit over time, and I don't want to pass because I have Zach. I want to make sure they get their spot. So this is one of the simulation of the, you know, circumbinary disk around the supermassive black hole ozone. I'm not going to go to the details here. Unfortunately, I don't have a lot of time. But you see that, you know, this goes for a long time, long dynamical times, many orbits, hundreds of orbits. And with a system of equations like the one we have, that's not an easy task. We have to be pretty strategic for how we do these things. So often we do split the problem where we do evolve the parts of the circumbinary disk first, where we excise this region from the computational domain, and we follow what happens around the circumbinary disk. And then what we do, we put back the black holes and look at what happened locally. And that's what you're going to see in some of these simulations of now. We call this strategy as end-off strategy. I'm going to skip this, but I want to say here that in order to do this simulation, you have to use not different strategy only, but different codes, because different parts of the computation domain requires different grids. Like, for example, in the circumbinary disk, for describing the long-term angular momentum transport, it's better to use spherical coordinates. And when you go down to describe, you know, the cavity region around the binary black hole, you want to use Cartesian coordinates and adapt mesh refinement techniques. Okay, so we have to do that in multiple days. The other thing I want to say about this is that people have been doing, because these problems are so intense in terms of calculation, people have been doing the simulation in 2D. Well, we don't do 2D, we do full 3D, we do the real thing. Okay, so that's a lot of course competition now, but you see that what we see in our simulations that really we have 3D structure. This is a polar view of one of the mini disks around the black holes. You see has a rich 3D structure. So there's no way you can really get the physics only doing 2D. Okay, so some of the earlier work with some of the graduate students, we calculated signal. You might see this online if you Google supermassive black holes. They all use these images. It's accredited to NASA, but it was my graduate student Dennis Bowen who did these simulations. So they did the PR. we did the simulations. Okay, so you'll see this, and I think this is pretty cool. You can see this is essentially show the light that you would see from, we post-process it, the simulation by following what photons would do, okay, in here. And we calculated a spectra and so on. You have the spectra here. I'm not gonna go over this because I want to show you the latest things. And I'm gonna go over about the radiation transport. This is very detailed. We can calculate light curves, okay? And these light curves you can see, well, here you can see the light curve over there is for two different systems. And you'll see that you see these blips, by the way. These things here, which I told you were soft lancing things, we actually get them. So this actually is a real observation down there. That is our simulation. So we got that. We got those. So if you wanted to make this as soft lancing, you're able to. Yeah.
You got the frequency up there. I don't work very well in frequency space, but
I
think that's X-rays.
Yes, that you are correct. You're correct. You're a trained mind. So, okay. So because most of the signal is coming from X-rays when we're down to, the mini disks in particular, okay? Right. Okay, so I'm gonna skip that too. I want to get into, maybe I can show this. No, I'm not gonna show this. I'm gonna show you some of the latest results. Okay, so this simulation goes, this is something that my graduate student currently hopefully graduating soon, Lorenzo Minoggi, who has done these simulations, where we look after I've done this very long-term simulation of the gas around the system. We're looking at what happens closed in. This was for two black holes that had equal mass and they were non-spinning, and you see they form these mini disks and they go around, and you see also they try to launch jets, but because they don't have spins in this case, there is no real jets, but they try to form something that is similar to a jets. And we went down to merger, and so let's look, this is M dot. Also be astronomer familiar with M dot. But one of the things that we discovered that M dot actually is not proxy for the luminosity anymore. Okay, because at the end of the day, you're going to see that towards the end, actually, in this simulation, you're going to get a lot of gas spread over after the mini disks disappear as the black holes merge. There's a lot of shocks and a lot of heating toward the end, and that produced this jump in luminosity, as the black hole merge. So you see that there is a jump in luminosity, and the luminosity, which is, I think, very new, this new results. We are writing the paper right now. Which is going to get probably, published, at least in the internet, in the archive, in the next few weeks. And so what I think, this actually the first talk where I did that you see there is a jump in the luminosity at merger, which we actually didn't expect. Okay, it's the luminosity is almost as loud as the earlier time where the thing was inspiring. So it's a large portion that comes on there, and these things were not even spinning. So that's pretty cool. There's a lot of mass that gets down in that region. As the black holes were, orbiting around each other, the gas from the circumbinary disk, it doesn't happen what they were saying. It actually follows. There's no decoupling. It follows the binary. It gets there. It gets so close that eventually there's no more room for these mini disks to exist. It destroys them. But then this gas gets down there. You see, there's a lot of shocks, heats, a lot. And then this heating produces, a lot of luminosity. So this is the mass, showing that the mass actually, it's a lot of mass getting down there, right? So, okay, that's, to me, is pretty exciting. Okay, so here, I'm showing something else. Okay, so this is about what happens to the electromagnetic field. And what we see here is that there is also, if you look at the fluxes of the field there, okay, so this is, you see that a lot of the field gets accreted, down the black holes, and that this field will tend to, move, most of the components you see are in the polar directions, you see. And some of the field gets accreted through the gas, as it gets over there, it straighten up and try to, form this field that tends to launch the jet. Okay, so, and you see that that is also responsible after the merger for allowed signal, this is the pointy flux, you can't relate that to jet emission. Okay, so, and again, this is not even with spinning black holes. So this is actually due to the gas swirling around. If you have spins are black holes that are rotating. Depends how fast they're rotating around themselves. So if they're rotating, how many of you know about the black hole sounding effect? Okay, so black holes that have spin have an ergosphere, it's called ergosphere. And an ergosphere has, in short, it will convert energy into, energy that can be launched for launching a jet. That will increase the energy so that it will launch it. This is thought to be the main mechanism for jet launching in supermassive. And you see that with different spins configurations, you have different, jet powers. Okay, so again, this is a simulation done by my graduate student, Lawrence Energy. And you see that there is different jet powers depending, the directions of spin. Plus means align with the orbital momentum, minus counterline this, positive, and then no spinning. And you see, most of the jet power comes when the spins are aligned. Okay, so this, I'm going to show you the simulation, what happens with this aligned spinning. Now you see, before you weren't seeing these vacated regions around the black holes in the polar view, but you see them now. These are actually caused by the jets that are pushing matter out and vacating the regions above and below. Okay, and you can see here kind of a system with two jets. Okay. Now, you will ask me, do you see the double jets? Well, this is a different question because the observations are kiloparsec away, and I'm looking here down here where the black holes are, okay? These jets farther away will get intertwined, and probably you see only one jet right here. So, but down here, you see two. And whether this motion is going to impart some kind of signal into the jets, and that will remain a kiloparsec away. That's a different question. It's very hard to answer that question because we don't have simulations there. But we have simulations tell you what happens here. What happens on merge? A merger, because the minute this disappear, the jets punch down. Okay. So how long that's going to last? I'll tell you, depending on the masses of the black hole, it can last hours, 2 years, decade. You're going to see the jet disappearing and then reigniting after merger. Again, this is unpublished, and we are going to pull out papers soon about all of this. It's pretty exciting. So it's the first time we're doing that. Yes, I'm going to wrap up now because I'm going to conclude here. I don't think I have much more to say, but I'm not going to say it. I have graduate students exploring, you know, things like what happens if the spins are not aligned, and that's pretty cool. And also graduate students exploring what happens if the masses are not equal and so on. And I think with Zach, we're going to be talking about jets, because I think there is quite interesting work to be done there. And we have a lot of interesting results in that direction. I'll leave Zach actually to continue to say what right now they have been working on. They have been warming up only, I would say, but that warm up, I think, is worth to see. Here's Zach. I think you need this. Oh, you sent me something.
Should have you through Google just so you wouldn't have to reconnect to the Zoom.
Okay, so I have an email.
Yes, you should.
This one.
Yes.
Oh, Zach, I need access. Okay. So you can ask questions in the meantime, Zach is What was the equation that the Boltzmann's equations? Yeah, it's not. It's a very complex. It's a 6-dimensional system based on distribution functions. So you need a little bit of. If you want to do that, go to a statistic course first, and then maybe quantum physics. You're done. Okay. Yeah.
Okay.
Sorry, I have a question. What kind of softwares do you use to run these simulations?
Zach is going to speak a little bit about that software, at least some of it.
A little bit, yeah.
Yeah.
All right, so I'm going to talk a little bit about what like my job has been throughout the summer and last semester, and a lot of it has been focusing on kind of doing three-dimensional representations of these simulations that Manuela was talking about. So first, I'll talk a little bit about the software, as Manuela just mentioned. So the software that we use is mainly something called Cactus. This is the simulation framework that we generally use. It's part of another project called Einstein's Toolkit, which has a lot of very useful physics-based computational software within it. And it's called Cactus because it generally has this central framework for how we understand physics and like how we're going to run these simulations. And then we're able to also add on these job-specific modules where we define the types of equations that we're going to be using to describe like the cooling within the disk, what type of disk we want, those kind of things we can all define within these modules that we call thorns. Personally, I was using PostCactus, which is a post-processing software for Cactus. It takes that outputted Cactus data and essentially allows us to resample it into a 3-dimensional uniform grid, just like a point cloud, where we can kind of get it into just Cartesian coordinates, where then we can input it into other software to be able to get the rendering started. So for the actual rendering itself, I used a fairly old software called the Visualization Toolkit, or VTK. VTK is a really powerful renderer. It allows you to essentially just input any sort of data and add in all the things you need, all the actors, which is like the gas and the black holes and anything else you want to add into it, as well as camera positions, where you want to see around the disks, the background, if you want to have like a galaxy background or any other type of thing. And it's useful because it has C and Python implementations. PostCactus is written in Python, and I was doing an integration between those two. So I was using it mostly within Python. Now, this is really the data that comes out of these simulations is massive. It's really, really, really huge. And even if we use post-cactus to sample it to kind of a lower resolution, then we still need some really, really powerful computing to be able to actually generate these renders. So far, I've been using RIT's research computing software, which is just a cluster available at RIT, as well as the supercomputer Frontera for higher resolution rendering. And I think that will be used more for rendering in the future. I'll talk about that in a second. So next, I'm going to show you some of the actual. Okay, well, that's not great. Okay, well, I was going to show you some of the simulations. I can try just getting that done real quick. Sorry about this.
Post merger, the data always looks pretty noisy there, but the models always look really flat. So I suspect that there probably is something in that besides just noise. Is there things like oscillations and there's so much angular momentum in the system? Don't they pick up like overtones or anything like that?
Okay, you know, you're asking a very good question because exactly this topic. Can I answer you after?
After, yeah, thanks.
So this is an example of one of the renders that I did. This particularly was of a simulation where the spins were unaligned, and that created some really interesting effects within the mini disks that we'll be able to see here.
Things that we cover, but
Oh yeah, and the spins. So essentially here, I'll just go over what we're really looking at here. Yeah. So what we're looking at is when we saw those big simulations before with the large circumbinary disk around the outside and the mini disks on the inside, we're looking at that cavity which holds the mini disks on the inside that's accreting the matter from the circumbinary disk on the outside. So we're just looking at that central cavity. The black holes are at the positions of those arrows, as we can see, and the arrows are pointing along the direction of the spin of the black holes. So we can see that as it accretes matter, then those mini disks start to form. And this particular simulation had strange mini disks within it, where they end up forming those like odd half moon shapes. And stuff like that is one of the big reasons why 3D rendering is such an important thing to be able to do in these three-dimensional simulations. Because when we're looking at a lot of times when we're looking at the visualizations of the data, we're just looking at two-dimensional slices of the data. And these three-dimensional representations make it a lot easier for us to see strange parts of the simulations or unique properties, such as these mini disks forming in only about half moons instead of forming the full disks. I think I'm gonna have to show this next one, fortunately.
it's like,
Because I have one more video here. So I'm sorry again about this. But dealing with that.
awesome.
That should have been granted.
What is asking me?
Access denied.
Right.
There we go. Okay. So this was one of the more messy, complex kind of movies that I ended up creating for this one simulation. We had an issue where there was a part in the jet stream that was starting to blow up as the simulation ran, and then the simulation would suddenly crash. So we wanted to kind of view it in 3 dimensions so we could see where that was happening and understand that. And just to break down this image a little bit, because there's so many things going on, you can see 2 different color bars. The one on the right is describing the circumbinary disk and the density of the gas within the circumbinary disk. And then the one on the left is describing the density of the gas within the jets. When we're looking at the actual image itself, then that kind of very faded middle part is where the circumbinary disk is, and you can see the same colors matching that color bar. And then the jets that we see are, of course, the jets. The bottom one is below the circumbinary disk. We just have the opacity really low on the circumbinary disk so that we can actually see through it to the jets. And then when we look at what the grid is in this, is essentially a grid to let us be able to see kind of distances within the simulation and understand where exactly along the jets, how far up the jets, where did it happen? And a grid like this is the best way we have right now just to understand distances if we need, to have a reference frame for that. And we'll see at the end of this that there starts to be kind of an explosion. It'll cut off really quickly as the simulation crashes, but we see that explosion there. And that's what we were trying to understand when we were looking at this three-dimensional rendering. Mhm.
That simulation was pretty great. And this was my APR simulation, where the demonstration was different. Yes.
Yeah, so that's a big benefit of these renderings, is that we're able to look at these issues that are causing in simulations. Of course, it's also very pretty, and it allows us to do, make some pretty PR kind of stuff to show the public what our simulations look like in a way that isn't just throwing numbers at them. And I'm looking for it. Yeah.
Like in the VR.
Yeah. So just to talk a little bit about the future work with this rendering and the future work I'll be doing. So with the rendering part of this, the future work that we really want to be working on is to parallelize the code so that we can use supercomputers like Frontera to get these really, really high resolution renders. You saw that those were a little low resolution. Those were very much like within the group trying to figure things out. But for PR stuff, we want to have these really high resolution images. So getting it parallelized will be really helpful for that. And then also, since part of the reason that we wanted to do this was just to make it easy for people to be able to do renders within the group, then I want to just finish cleaning up the code for ease of use, just add some more comments and things to make sure it's readable. Now, for the future, the work that I'll be working on with Manuela is specifically simulations of relativistic jets. And she talked a lot about how important those were, but they are a big part of the simulations, and it's really important to have a full understanding of these. They are very, supermassive binaries are some of the most violent places in the universe, and these jets, are a big part of those interactions, and it'll be really interesting to see, more about it. And that's it. Yeah, that's it.
Or unless you want to see more.
So now,
Maybe
Plus.
you can stick around a few minutes, folks might come down and ask more questions, but maybe others will be move on.
there was a question about the,
Right, post-merger, yeah.
so the post-merger. So actually you're asking a very cool question. Spot on, because I don't know if it's, so what we are, so you saw some variation in the post-merger signals. That's what you saw, right? Yeah, I'm looking at that. And it turns out, and I haven't mentioned in my simulation, that there is indeed in the circumbinary disk, we see due to turbulence, we see a generic feature, overdense feature, being present. That overdense feature interacts with the accreting gas, but it also it interacts with the accreting gas, and it seems to last through the entire spiral, but also merger and post-merger. This is pretty new. It's actually something I discussed just with my graduate student, my collaborator, just a few days ago. We see that over density